So again, my name is Carl Schmidt. I'm speaking to you from the University of Virginia in Charlottesville, United States. And I wanted to thank you guys for inviting me to give this talk here. I'm going to talk a little bit about the different escape processes that are happening in our solar system from planets and moons. So you should be able to see my screen if I do that there. And if that's coming through okay, I'll go ahead and start.
Yes, we can see your screen. We're just trying to put it on full screen, and just give us just a second.
Sure. Yeah, I guess if they don't mute themselves, the buffering makes a delay.
I think you can start. I think now it's okay.
Okay, thank you. So I'm just going to talk to you a little bit about escape processes happening in different atmospheres throughout our solar system. The first question, of course, is why should we care about atmospheric escape? Well, the escape conditions on a planet and a moon tell us how it's evolving with time. So knowing the current escape conditions can give us a window into what that planet was like in the past, and also what it would be like in the future. So it's good at explaining why the planets and moons are the way they are today. And of course, atmospheric escape is just an interesting topic. So some of you more animositous viewers might say, okay, well, I still don't care. Prove to me that I should care about atmospheric escape. And atmospheric escape has a lot to do with how Earth is really nice the way it is that we enjoy it right now, why all the planets that we observe in our solar system are so different. When the sun blows up and becomes a red giant, if we're still around a couple billion years from now, we're going to need a nice place to go. That explains why Mars is red, why Venus is hot and cloudy, and why the gas giants are so gassy. And if one of all these exoplanets that we're observing might finally be habitable. So I wanted to make a distinguishment up front between neutral and plasma escape. Neutrals, which are atoms and molecules, only interact with gravity and the other particles around them, whereas plasmas, ions, and electrons will also interact with magnetic and electric fields. In practice, most of an atmosphere is composed of neutrals, so most of that loss into space is composed of those neutrals. So just sort of stepping through Earth's atmosphere here, weather occurs in the troposphere at about 10 kilometers, and the atmosphere cools as you increase in height. And it's pretty cold on the tall mountains, so the temperature here is shown in red. Mount Everest is just beyond this layer that's in the troposphere, and at around 10 to 12 kilometers is where commercial jets fly, and you actually occasionally see birds at that altitude. A bar-headed goose will fly over Mount Everest. Above this height, absorption of ultraviolet light results in ozone being consistently broken apart and reformed, and that heats the atmosphere. In the mesosphere, the atmosphere cools again as less ultraviolet is absorbed by the ozone. The average meteors burn up in the upper mesosphere, generating metal layers where they vaporize. At about 105 kilometers, the constituents of the atmosphere begin to separate, and molecular diffusion begins to dominate over the turbulent diffusion. This is called the homopause. The atmosphere above the homopause is no longer well mixed, as the heavy molecules separate from the lighter ones. This is also about the height where far ultraviolet radiation breaks apart the molecular oxygen, O2. This UV produces one plasma layer in the ionosphere, and another layer is produced higher still where atomic oxygen is broken apart. The region from about 100 to 500 kilometers is called the thermosphere because absorption of high-energy photons from the sun results in very hot temperatures. As such, the upper atmosphere of the Earth varies quite a bit with solar activity. Satellites in low Earth orbit often occupy this thermosphere, but even about 500 kilometers, atmospheric drag is a problem. So the Hubble Space Telescope and the International Space Station need a boost from time to time, or else they'll simply fall down. So what have I labeled up here as the exosphere? Where do things start to escape? Well, it all has to do with where particles collide. So in a local approximation where temperature and gravity don't really change much over altitude, the density and pressure fall off exponentially with distance from the planet's center r. The rate of the exponential fall off is called the scale height here, and we define everything in the portion of the atmosphere and a region that can escape as where the mean free path of an atom between collisions is larger than that scale height. So if you imagine a molecule moving through a background of other molecules, you can sort of define this cylinder in which collisions were happening. So this L is called the mean free path. The term on top is the distance that atom will travel during time delta t, and on the bottom is the atoms per unit volume, n times the volume of that cylinder. So when that mean free path for any arbitrary size cylinder exceeds the scale height, the atmosphere is effectively collisionless and escape is possible at the top of the atmosphere. So how do we go about actually measuring escape? Well, before spacecrafts were flying through atmospheres, astronomers estimated atmospheric escape just with light. If you imagine light getting absorbed by an atom, it's going to make that electron in the atom's orbital shells around the atom jump to an excited state. And then at some time later, that light is going to get re-radiated by the atom, and some of those photons are just going to happen to fall on your telescope. The amount of light that you receive at a specific frequency can be related to the density of atoms. The distribution of the densities in the atmosphere can be used as a proxy for atmospheric escape. The sometime later part varies quite a bit. In the case of hydrogen Lyman alpha, it's nearly a billionth of a second. But in the case of the hydrogen 21 centimeter, it's about 10 million years if the atom doesn't interact with something else first. In actuality, this is sort of a simplified picture. The things which excite atoms and molecules don't always have to be light. They can be collisions with other atoms as well. And there's generally some other stuff between you and your atoms of interest. So I wanted to give an example here that's the solar spectrum, and I wanted to emphasize that what we observe in the visible part of the solar spectrum is actually a very, very small portion of the light that's going out there in space. So we observe from about 400 nanometers up to about 700 nanometers in the visual part of the spectrum, and if you blow that up in a picture of the sun as a function of wavelength, you get this image within a shell spectrograph from the National Solar Observatory. So all the trace elements in the surface of the sun's atmosphere actually cause different absorption features in the solar spectrum. So the hydrogen at the surface of the sun gives you an absorption line here at 4861 angstroms, and there are small amounts of heavy metals in the sun's atmosphere that cause absorption lines too. Iron, magnesium, there's a sodium doublet at 5896. The H-alpha line is 6563. A molecular things in the sun's atmosphere will have rotational and vibrational states so that you get a whole slew of absorption features from those. So it wasn't until the 70s and 80s that we got our first view of the Earth in ultraviolet light, which is largely attenuated by the Earth's atmosphere and doesn't make it to the ground. So this is a little overview of what the Earth looks like from orbit in the ultraviolet light. So on the bottom left there is astronaut Charles Duke from Apollo 16 in 1972, and he's got an ultraviolet camera set up there that's pointed back at the Earth, and it takes that picture just to his right. The Solar Dynamics Explorer, the Dynamics Explorer 1 spacecrafts that orbited the Earth took the photo on the right in about 1980, and it seems the same emission. So the auroral oval that generates the aurora that you can see at high latitudes from the Earth can be seen in oxygen 1304 emission. That's oxygen ions that are recombining and emitting that light. And then the big cloud that extends over the whole Earth is called the hydrogen geocorona, and that can be seen at 1216 angstroms and Lyman alpha. Now some of that material is escaping, but not all of it. So in order to escape, it needs to be moving pretty quickly. So space shuttles and hydrogen atoms both need about the same velocity to escape the Earth. However, a collision with another particle will bounce a hydrogen atom off course, whereas the space shuttle will plow right through. So if you set the kinetic energy anywhere above the Earth equal to the potential energy, you can figure out what the escape speed is. From the surface, a space shuttle would need to go about 11.2 kilometers per second in order to leave the Earth. But hydrogen leaves from the top of the atmosphere, so it's a little bit less there. It needs to be going faster than 10.8 kilometers per second. Now, because of collisions, the velocities of atoms in an atmosphere will obey what's called the Maxwell-Boltzmann distribution that I've shown in red here. If you take that distribution and integrate everything that is above 10.8 kilometers per second, you can determine what's called the Jeans escape flux. And that's atom by atom, how many atoms are sort of trickling out of the atmosphere because they just happen to be going at a high enough speed, and they happen to be at a part of the Earth's atmosphere which is collisionless. So I wanted to talk a little bit about some non-thermal escape mechanisms. Jeans escape isn't actually sufficient to explain all the hydrogen being lost from the Earth. The main escape mechanism is thought to be charge exchange. If you have a proton that is trapped in Earth's magnetosphere that bumps into a hydrogen atom, it can actually swap an electron with it, and you get a very energetic neutral back out. There's another mechanism called the polar wind, where these electrons that are precipitating down and causing the aurora can actually pull protons out of the ionosphere in order to balance the charge. These are both very energetic mechanisms, and the associated hydrogen has no trouble escaping. In a Jeans type escape, the energy at the exobase limits how much of the atmosphere is lost. If the energy is no longer a limiting factor, then the escape is instead limited by how quickly hydrogen can diffuse through the homopause layer around 100 kilometers. That means that the mixing ratios of water and other molecules around this altitude sets the maximum escape that can occur. Currently, the rate of escape of Earth's hydrogen is about 3 kilometers per second, and it's limited by how quickly it can be supplied from below. This hydrogen initially comes from water and methane, but it may have been different in the past when the sun was a lot more active, or before plants began to fill the Earth's atmosphere with oxygen. So which gases can actually escape from these different planets in our solar system? Each body holds on to the elements differently. Because of its mass, the average speed of a water molecule is about 4 times slower than that of a hydrogen atom at the same temperature. Note that the oxygen here is heavier because the oxygen usually exists in O2 molecular form, so that's actually heavier than water. So the relative escape rate for the planets becomes rapid when the temperature in the upper atmosphere is high and the relative gravity is weak. So Pluto and Titan are both good examples of that. And for instance, Mars will lose most of its hydrogen and helium over geological timescales here, but just barely hang on to water. Now, because photochemistry in the upper atmosphere is complicated, the temperatures in the upper atmosphere are not always intuitive. So Venus is the hottest planet in the solar system, but the other upper atmosphere is relatively cold, about 350 K. Mars and Venus have carbon dioxide-dominated upper atmospheres, and that is very efficient at radiating away energy in the infrared that cools the upper atmosphere. The temperatures of the upper atmospheres of the gas giants, like Jupiter and Saturn, should only be about 200 Kelvin or so due to solar heating. But the measured temperatures, however, are more than twice that hot. There's no real consensus on why this is so. But one theory is that gravity waves propagate upwards through the atmosphere and deposit energy when they break. An alternative theory is that the heat comes from the high energy electrons in the aurora of these big gas giants. But it's difficult to spread that heat around the planets efficiently, and this would heat the poles, but not the equator. So if we look at Venus a little bit more closely, whereas Jeans escape is the dominant atmospheric loss in certain places where atmospheric loss is sort of evaporating molecule by molecule, the heated air can also flow as a wind. So if an upper atmosphere can absorb ultraviolet sunlight, warm up, and expand, it will push the air upward. And as the air rises, it can actually accelerate smoothly through the speed of sound, and then attains an escape velocity. This is more or less how the solar wind works in Parker's model. This form of thermal escape is called hydrodynamic escape, and there's evidence that it's occurred on Venus. So the Venus Pioneer Venus mass spectrometer gives a deuterium to hydrogen ratio of about 1 to 50. And that's 120 times what the ratio of hydrogen that has an extra neutron is at Earth. So that means that if Venus started like the way Earth started with the same material, it's lost about 99% of its water since it was created. The hydrogen that gets lost over time is actually a tracer for water, because methane, ammonia, and water are usually the most commonly found sources of hydrogen in the atmosphere, and given its distance from the sun, it's likely that this hydrogen is probably a tracer for early water on Venus. Now, because the rapid hydrogen loss would drag water with it, but not carbon dioxide, and a couple of different models have shown that, carbon dioxide actually built up in Venus's atmosphere, and because there's no water like there would be on Earth, there's no chemical reactions that would convert that into limestone and actually hold it in the rocks. And with carbon dioxide building up in the atmosphere of Venus, there's sort of a runaway greenhouse effect that makes Venus the very hot and miserable place that it is to live today. The current escape on Venus is probably not hydrodynamic anymore. Instead, it's charge exchange like it is at the Earth. And also atmospheric sputtering, where an ion comes in and hits a molecule and actually sputters off a smaller atom. So there's pretty good evidence all around that water was clearly present on the surface of Mars at some time in its history. And it also has that enriched heavy isotope ratio that indicates that a lot of escape has occurred. And carbon dioxide is building up in Mars' atmosphere. So carbon dioxide is currently most of the atmosphere of Mars. Most of that hydrogen that has escaped also initially came from water like it did on Venus. And when the hydrogen escapes, the oxygen can be left behind. So this is why Mars is actually the color that it is today. If you imagine all that oxygen, it's mixing with different minerals in the soil and oxidizing them, so it's effectively rusted it into the red planet. The current escape is most likely due to photoionization, where you're actually losing ions rather than neutrals, and also dissociative recombination. So when a molecular ion finds another electron and becomes neutral again, it can split that molecule apart into individual atoms, and then those get lost because of their high kinetic energy. And atmospheric sputtering also happens on Mars. So there's a mission that will launch in November to go examine the Mars upper atmosphere. And one of the reasons that this mission was sold to NASA is because it's going to measure the deuterium to hydrogen ratio, again, that heavy water to water that has a massive, or I'm sorry, the heavy hydrogen to the hydrogen that has a massive 1. And just to sort of show you how difficult that measurement is to make, this is sort of a prediction of what the spectrum is going to look like around this Lyman alpha hydrogen line. The shift to that heavy hydrogen as opposed to normal hydrogen is only about 1/4 of an angstrom, and it's sort of a bump on the wings of the distribution. So this is a very difficult measurement to make, and that's why it hasn't been done before. So I wanted to also talk a little bit about radiation pressure and resonance scattering. This does some pretty interesting things by pushing on atoms and accelerating them away from an atmosphere. So if you imagine a photon being absorbed by an atom, well, that photon had an initial momentum that's just h over lambda. And it gives the atom a little bit of a kick in the direction away from the sun. When that atom subsequently releases that photon, it probably does it in an isotropic sort of random direction. So it's getting a kick in one direction, but because it's releasing that photon in random directions, the net effect sort of cancels out in the direction anti-sunward. So if you take a look at what the change in momentum is over time, that's actually a force. And if you consider all the different scatterings at all the different wavelengths and how often scatterings occur, you can back out the radiation acceleration. At Earth and Mars, for the hydrogen that's escaping, that radiation acceleration is only about 1 centimeter per square second, and it forms a slight geotail. So the actual atmosphere at great distances from Earth and Mars is slightly asymmetrical. For Venus, because it's closer to the Sun, the atmosphere is significantly asymmetric, and this radiation acceleration actually has a small contribution towards the hydrogen loss. For sodium in an atmosphere of Mercury, the effect is actually extreme, and it drives atmospheric escape, as shown in this diagram here. And that's because Mercury is so close to the Sun. And sodium is sort of a special atom. So Mercury and the Moon both have this very extended sodium tail. And if you take a look at the top right diagram, that's a picture of Mercury over a 7-degree field of view. So that tail that's extending behind the planet is more than 1,000 times the size of the planet. And because Mercury is so close to the Sun, you can only really view it at dawn or at dusk. So that's actually a tree that is the fuzzy object sort of in the bottom bright portion of that field of view. And there's one fewer of those trees down at the McDonald Observatory now because I actually had to saw one down when I was working on my PhD taking this data. The Moon also has a sodium tail that's escaping the lunar atmosphere, and it does something pretty cool. When it sweeps past the Earth's gravity focuses the trajectory of all of the particles that are crossing it. So this was first actually observed in all-sky cameras that were looking at mesospheric sodium in the Earth's upper atmosphere. And they saw this little spot that happened about once a month at new moon. It was later determined that that spot was actually backscatter from sodium in the moon's atmosphere as that tail was sweeping past the Earth. If you look in the direction opposite the moon, you can sort of see this fuzzy spot due to backscatter from sodium in the sky. So how do we get these really heavy elements like sodium escaping the atmospheres of Mercury and the Moon? Well, an exosphere is simply the part of an atmosphere where the collisions are rare between atoms. In the case of Mercury and many of the moons in our solar system, the entire atmosphere is an exosphere. So the composition of these atmospheres are more representative of what the minerals are on the surface. There are a few different source processes that eject these molecules from the surface into the atmosphere. You can have ultraviolet sunlight release them, as is shown in the top diagram. You can have an ion which will impact the surface and sputter things off. And you have meteoroids that are constantly impacting the Moon and Mercury and other moons that will vaporize the rocks on the surface. Those meteoroids are smaller than we get on the Earth because there's no atmosphere to burn them up, probably about a micron in size or so. And because these are all non-thermal processes and there's no collisions in these atmospheres, you can't really define a temperature for bodies like this. So for instance, Mercury has a pretty small magnetic field. The plasma from the solar wind and the planet itself gets trapped in that magnetic field and directly impacts the surface near the poles. This is probably responsible for the bright sodium emission that can be seen at the poles in this purple image. However, the laboratory measurements indicate that the ions impacting the surface are insufficient to directly generate as much of an atmosphere as we observe. One theory is that the sunlight generates the atmosphere, but that there's more supply in the surface areas that have been exposed to a lot of plasma. The details of how this works are not well understood yet, so this is a subject of active research. Ganymede also has a magnetosphere that is within Jupiter's magnetosphere, which itself is within the Sun's magnetosphere along with the rest of our solar system. In this case, the surface has a lot of water ice, and while rocky bodies like Mercury have a lot of sodium, magnesium, calcium, and other minerals in their atmosphere, an icy body like Ganymede has mostly oxygen, since impacting ions can break the oxygen away from H2O. The aurora on Ganymede is the same 1304 and 1356 angstrom emission that we saw in those previous images of Earth's aurora in the UV. The problem is that at Ganymede, energetic electrons plow through and hit the surface instead of being stopped by the oxygen atmosphere like they do in Earth's aurora. As such, we're not entirely sure what generates the auroral emission on Ganymede, but the current theories include field-aligned currents or heating from plasma oscillations. This is another subject of active research. Io is one of the most interesting bodies in the solar system, without a doubt. Jupiter is such a massive planet that the tidal forces on this tiny moon cause volcanic outflows at about a ton per second. The New Horizons mission, as it flew past Io in 2007, took this snapshot of one of these volcanic plumes going off that you see on the top left. The actual substance that comes out of these volcanoes is mostly sulfur dioxide, which is the same smelly ingredient that's in farts and rotten eggs, and it's pretty gross stuff. Dense plasma rotating with Jupiter around 70 kilometers per second slams into this sulfur dioxide and ionizes it. So the sulfur and oxygen ions get trapped in Jupiter's magnetic fields, and because the magnetic axis is not exactly aligned with the rotation axis, the whole system forms this big wobbly plasma donut with about a 10-hour rotation period. So when Cassini flew by in 2000, it observes this sulfur plus and oxygen emission sort of wobbling around Jupiter, and you can see this big plasma torus of sulfur and oxygen ions wobbling around the whole system. There's a small amount of sodium sulfate that's also present in these volcanic plumes, and you can see that in the bottom left image. The sodium cloud that's pointing horizontally is due to the atmospheric sputtering of the sodium sulfate that volcanoes eject. The tilted cloud is produced by dissociative recombination of sodium and the torus molecular clouds. When the sodium is neutralized, it's flung from the system, and it forms a giant nebula that extends for several hundred Jupiter radii. So that's another massive sodium object in the solar system. There's a moon on Saturn called Enceladus that's quite similar to this. And instead of sulfur dioxide being ejected, the moon on Saturn actually has water vapor that's being ejected into Saturn's magnetosphere. That moon's called Enceladus. So this is a common phenomenon. Another moon of Saturn that's an interesting place is Titan. Now, the Titan isotope ratio of nitrogen suggests that either a large scale atmospheric escape has occurred, or that Titan's original material had an isotope ratio that's closer to that of comets. It has a methane cycle just like Earth's water cycle, so there's lakes of methane on the surface, like you can see in the top right diagram. That's reflection off the surface of a lake of sunlight, just like you would reflect off of a mirror. So methane rains back to the surface and fills these lakes, and then it evaporates back into the atmosphere. The overall density of the atmosphere is actually much greater than the density of the Earth, and the Cassini spacecraft has flown past Titan and actually flies right through the atmosphere. It's done about 80 flybys so far. There's a pretty substantial degree of variability in terms of the density and the temperature in these atmospheres, and a lot of different modeling has been done to try and figure out what the atmospheric escape is like. So some of the data from one of that flyby is shown on the bottom left panel. The homopause, where the different constituents of the atmosphere start to separate, is at about 1,000 kilometers, and above which you can see the hydrogen separate from a constant mixing ratio and take on its own scale height. The exobase is at about 1,500 kilometers, and the hydrogen dominates the atmosphere much above this height. Plasma from the magnetosphere deposits a lot of energy into the atmosphere, but sunlight probably dominates escape. The hydrogen escape is diffusion limited, just as it is on Earth. Some models have predicted that the methane also escapes at the diffusion limited rate. In this case, an entire atmosphere of methane would be lost over geological timescales. Methane is also destroyed by sunlight, and its overall budget on Titan is the subject of much debate. Thus far, no sodium thus far no carbon-bearing ions in Saturn's outer magnetosphere have been detected by the other instruments on Cassini that would be consistent with large methane escape predictions. And several simulations show that methane escape is probably closer to what the gene's flux would be. So finally onto the exoplanet. Pluto has a nitrogen atmosphere that's just like the Earth and Titan, but has a very elliptical orbit. So there were some predictions that said that when Pluto is far from the Sun, the atmosphere would completely collapse down to the surface. Just this week, Kathy Olkin and Leslie Young and some co-authors published a paper saying that there's ice on the surface that is consistent throughout the whole orbit of Pluto, and that the atmosphere probably doesn't condense as it orbits the Sun. Everything that we know about this atmosphere is due to stellar occultations when there's a star behind the system and Pluto passes in front of that star. So we don't know a whole lot about the atmosphere. The exobase, where things start to become collisionless, is not really certain, but different models have put it between 3 and 8 planetary radii. So this spacecraft on the bottom left is called the New Horizons mission, and it's going to arrive in July of 2015 at Pluto. Now, because Pluto's so far away, the spacecraft is moving pretty quickly to get out there, and the planet Pluto doesn't have enough gravity to slow the spacecraft down, so there's no orbit, it just does a flyby, and it takes all of its data on the Pluto system in just a couple of hours. And it's going to look at the atmosphere the same way we do with starlight by going into Pluto's shadow and facing back at the Sun and looking at how much light has been absorbed by the atmosphere. And if we're lucky, it's going to pass through the shadow of a moon called Charon. And there's some evidence in different models that some of the atmosphere of Pluto is actually collected around Charon because it's a pretty big moon. So just some concluding remarks here. There's now, as of today, 732 different exoplanets and more than 3,000 candidates that have been discovered. And that's a lot of new atmospheres to try and learn about. There has been escape seen in some of these atmospheres, including hydrogen, carbon, oxygen, and sodium. So this is a really good time to get involved in planetary science. I wanted to give a sort of partial list of the different things that are on their way to planets and bodies throughout our solar system. LADEE has just launched on its way to the Moon. Messenger is currently in orbit around Mercury. Mars Science Laboratory is on the surface of Mars. There's Venus Express, and Cassini has been taking data for almost 10 years now at Saturn. There's lots of other missions up and coming, and this is an image that's actually happening right now as I speak of the different science instruments that are orbiting the Earth. So on this time scale, 1 second is 15 minutes, and you can see how many different objects there are out there taking data. This is just the things that NASA has ephemerides in their NASA Eyes on the Solar System for. But there are many, many objects currently orbiting the Earth that are in the space environment. And a lot of them are doing good science that's planetary science. So I'll finish there, but I wanted to leave you with a couple of thoughts on Mercury that have to do with all these exoplanets, because the exoplanets are very close to the Sun. These planets are going to be bathed in radiation that comes from their host stars. So the top movie was taken with the stereo spacecraft, and this is actually pointed out to us by an amateur astronomer in Australia, who's a medical doctor by day, and he just sort of hunts for comets in the stereo data by night. So you can see that that's clearly having an effect on Mercury's atmosphere, and you can see a sort of fuzzy trail of the exosphere escaping behind it. And below that is an image from the TRACE instrument, which is taken in ultraviolet light, showing what a tenuous place and the hazards of being that close to a solar environment are. And so I'll stop there and take some questions.